Okay, 3.2 is all about differentiability. This is kind of like continuity. Now we're talking about differentiability. So don't be freaked out. This isn't a bad thing. Think back to when, and you don't have to write this, but with continuity, there were 4 types of discontinuity. Let's think of the 4 types of discontinuity. First, removable, jump, infinite, oscillating. These are the 4 types of discontinuity. When we talk about differentiability, there's also going to be 4 types of non-differentiability. Okay, that's a whole big mouthful, but it's just going to be like this stuff. We're just going to do the same thing again for differentiability. All right, so the first type of not differentiable is a corner. Absolute value is an example where it is not differentiable. Now, it can be continuous. Notice I don't even have to pick my pencil up. This is a continuous function. But if there's a corner, because think about this, what did we say the derivative represents? The slope at that point. So think about the absolute value of x. What's the slope on this side? This is a -1 slope. Here, 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 all the way along here. What about this side? This is a +1 slope, all the way. So that means my derivative on this side equals 1. My derivative on this side equals -1. Well, what is it at 0? The left is -1, the right side's +1. We say that it is not differentiable at a corner because the slopes change at that point. Okay, now if it's curved, it's gradually moving. So curved is okay. A corner is not okay. All right, number 2 is a cusp. I call this, you remember when you were a little kid and you draw birds in the air like this? Okay, this is a cusp. It's like this. So this is our picture of a cusp. A cusp is where the slopes of the secant lines approach affinity from one side and negative infinity to the other. So you can recognize a cusp if you have an exponent of an even over an odd. If the exponent is even over odd, that will be an example of a cusp every time. Number 3, a vertical tangent. So think about the cube root of x. X to the third is straight up and down. Cube root is sideways. This is a vertical tangent. And 4, if there is any kind of discontinuity, a jump, removable, infinite, oscillating, any of the 4 types of discontinuities, that causes it to be not differentiable at that point. So all of these 4 fit into number 4 of the differentiability. All right, so if we think of this graph, I'm going to shift to the right 2, up 3. What's the shape of absolute value? Just our V. Now, we find all points where it is not differentiable. When you are listing points, it's not a coordinate point. It is at the x coordinate only. X equals 2 is a corner, therefore not differentiable. So if you see any of the 4 pictures from before, that's where it's not differentiable. Okay, so differentiable implies local linearity. Basically, it means if you would zoom in on any part of this curve, you would see a straight line. think about the absolute value, a corner, you'd see a dot. You'd never see a straight line no matter how close you got to it at that point. We're just not even going to worry about any of this part. The one thing I am going to do is teach you how to use the calculator. So if you get your graphing calculator out, sometimes it'll say in the book, enter. That means use your graphing calculator. So on your graphing calculator, you want to do Math 8. Math 8 is using your graphing calculator to find a derivative. Now, you can't do this with most stuff, but you're going to get to a point where that's the only thing you can do for some things, or you can use it to check for others. But, so what we're going to do, you see D, and there's always a little cursor here you have to fill in. This always is going to be X. Every single time you're going to put an X there. This is where you put the function. So in this case, the function is X to the third. The function goes here at X equals the numerical value 2. So this is what you should see on your screen. You're going to hit enter. And I don't know what it starts. And it just underneath 12. Now, I don't know why. It should just be 12, and you'll see why next week. But the 0.000001, you really just need 12. Okay. Now, if we look at this, sometimes this is, so let's do our Math 8 again. Put in X, and then put the absolute value of X. So go to Math, over to Number, abs X at 0. We already said that's a corner, right? The graphing calculator doesn't catch everything. It thinks our corner is kind of like a curve. It's saying it's a 0 slope. This is not differentiable. So see, you've got to know more than the calculator here. You've got to recognize this is not what the calculator says. Okay, so this theorem we're going to talk about a lot throughout the next year. If a function is differentiable, then it has to be continuous. That's all this theorem says. And so anytime you're given a function that states it is differentiable, you know that it's continuous. That's all this is saying. And this is just the intermediate value theorem for derivatives. It's the same exact thing. If you have f prime of A and f prime of B, then everything in between is also a value.